This fruit should not be this easy to buy. A pristine supermarket strawberry is the final product of an invisible, high-stakes war against time and thermodynamics. To reach a shelf in perfect condition, this berry must survive a 1,000-mile journey through a precision logistics system built specifically to fight heat and decay. The logistical challenge begins with the biology of the fruit itself. Strawberries are non-climacteric, meaning they do not ripen after they are picked. They lack a protective outer skin and rely entirely on a rapidly depleting set of internal metabolic reserves to survive the transition from the field to the store. Those reserves burn up quickly because of metabolic heat. Harvested strawberries sitting in an 80-degree field respire aggressively, generating roughly 41,800 BTUs of heat per ton every day. Without intervention, they effectively cook themselves from the inside out. In logistics, this threat is quantified by the hour-to-day rule. Every single hour a strawberry sits in that ambient field heat permanently destroys 1 full day of its retail shelf life. The decay accelerates the longer that heat remains trapped inside the fruit. Achieving year-round availability required a $1 billion invisible supply chain. This network is engineered specifically to artificially halt the process of biological decay, extending a few days of life into several weeks. The first node in that network is the pre-cooler. Placing a pallet of warm strawberries into a standard cold room is an engineering failure. Stagnant boundary layers of air around the packaging act as thermal insulators, allowing the center of the pallet to retain its heat and rot within hours. To solve this, facilities use forced air cooling. As this animated cross-section shows, a static pressure differential is applied to the stack. Chilled air is pulled directly through the ventilation slots of the plastic clamshells, physically extracting the internal heat from the fruit. This process is measured by a strict mathematical target, the 7/8 cooling time. The system must remove 7/8 of the field heat difference within 2 hours, plunging the core temperature to just above freezing. Stopping precisely at this threshold prevents the high-velocity air from dehydrating the product. The pre-cooler acts as a precision brake pedal for the fruit's metabolism. It halts decay by extracting heat without accidentally destroying the marketable weight of the product through water loss. Once the field heat is extracted, the cargo moves to the highway. It is a common logistical misconception that refrigerated trailers, or reefers, are designed to cool down produce. In reality, these units are engineered strictly to maintain existing temperatures. Loading warm fruit, or leaving the refrigeration unit running while the trailer doors are open, causes the system to fail. The pressure differential draws in humid ambient air, which immediately freezes over the evaporator coils. This ices over the system, forcing it into a defrost cycle where no active cooling occurs. To maintain thermal integrity, the internal geometry of the trailer must be perfectly configured. This diagram highlights the mandatory ribbed T-rail floor and the ceiling air delivery chute. These features ensure that chilled air can circulate uninterrupted above and beneath the load. Loading pallets requires strict adherence to spacing rules. As seen in the bottom right diagram, the load must be centered to prevent the conduction of outside heat. This creates a continuous insulating airspace between the cargo and walls, ensuring fruit never touches the exterior. This airflow geometry is only effective if the pallets are immobilized. This diagram shows the use of load locks and sidewall airbags. These tools secure the square grid of pallets, preventing them from shifting and blocking the parallel air channels during transit. A refrigerated truck is a mobile thermodynamic vacuum. It requires perfect internal architecture to maintain the cold chain over a 3,000-mile journey. Upon arrival at a regional distribution center, the strawberries enter Group 1 storage. This environment requires an absolute temperature hold at 32 degrees Fahrenheit, with relative humidity between 90 and 98%. Beyond temperature, the facility must manage a chemical threat, ethylene gas. Distribution centers aggressively partition strawberries away from climacteric fruits, such as bananas or tomatoes, which naturally emit ethylene as they ripen. Even trace amounts of ethylene can trigger rapid mold decay in berries. To prevent this, facilities use active potassium permanganate scrubbers and outside air ventilation to neutralize the atmosphere. The distribution center functions as an active chemical and thermal quarantine zone. It is the final firewall, ensuring the fruit is stabilized before it ever reaches the retail shelf. This infrastructure is a response to the brutal financial realities of the agricultural industry. Waste begins in the field, where 36% of all cultivatable strawberries are left to rot because they fail to meet rigid cosmetic specifications for size and shape. At the retail level, the financial drain continues. Supermarkets discard up to 9% of the strawberries they receive. Consumer expectations are so high that retail employees must throw away an entire clamshell if even a single berry shows a trace of mold. The cold chain is a financial risk mitigation tool. Investing in high-efficiency cooling to drop post-harvest loss rates from 15% to 10% compounds into massive revenue recovery for agricultural cooperatives. The industry invests billions in temperature control because freshness is an economic metric. Protecting the razor-thin profit margins of the fresh market requires halting biological decay as early as possible. Modern engineering is now pushing beyond basic refrigeration to extend shelf life. Researchers are developing edible nanocoatings made of zinc oxide and chitosan. These microscopic layers physically block pathogens and stimulate the fruit's own internal antioxidant enzymes. These advances are paired with active modified atmosphere packaging and AI-driven ordering algorithms. These systems analyze weather trends and sales data to prevent supermarkets from over-ordering and allowing stock to age out. A carton of strawberries is a physical manifestation of high-precision thermodynamics. The price at the register covers the labor of the harvest, but it primarily funds a global network of specialized engineering. Every berry represents an expensive, multi-stage effort to stall biological decay. The success of the modern supply chain lies in the ability to hide this complexity. It takes a nearly impossible logistical triumph and makes it look entirely ordinary.